Welcome back. In section 8.2, we get to work with the law of sines. So we'll start with an oblique triangle. And we'll label the angles cap A, cap B, cap C, and their respective opposite sides, lowercase a, lowercase b, lowercase c. And what we'll do is we'll take this figure, we'll construct a perpendicular on it. And we'll call that H since it is the height of the triangle under this orientation. So here's side C, here's side A, here's angle cap A, angle cap C. And some relationships that we know. Looking at the triangle on the left side only, I know that the sine of A would be the opposite over the hypotenuse. Looking at the triangle on the right side, sine of cap C is also opposite over its hypotenuse. We'll notice there's an H in both of those, so let's get the H by itself. So H is worth C sine of A. H is also equal to A sine of C. Since they're both equal to H, they must then be equal to one another. So C sine of A is worth A sine of C. And divide all sides by CA. This is a lowercase c here. And we have sine A over A is worth sine C over C. So we have established that relationship. If we rotate it, and let me go ahead and draw the rotated triangle. So here is angle C, here's angle A up here, here is angle B. And again, I want to drop a perpendicular. Sometimes I might have to do that outside. We've already used H, so we'll call this guy H prime. So let's see, we have side B, side C, right angle there, and angle here would be pi minus B, since that's 180 degrees is a straight line, so take off angle B. So what we know from that, we can definitely find sine of C here. So sine of cap C would be opposite over hypotenuse. And I can also look at this smaller triangle on the end where I drop the perpendicular and say that the sine of pi minus B is worth H prime over C. So like the last one, we can get the H primes alone. So H prime is worth B sine of cap C. H prime is also worth C times the sine of pi minus B. And here we can use some of our chapter 7 properties on the second equation. So C times, and then sine of A minus B is sine A cosine B, so sine of pi cosine of B, and then we keep the sign in the middle, so minus sine of B cosine of pi. So they just switch of which one has the sine, which one has the cosine. Now the sine of pi, though, is 0. Goodbye to that term. That will 0 out. So I can say that h prime is c times the opposite of sine of b, and cosine of pi is -1. So two negatives will flip that guy positive. So h prime is c sine of b. Each one of these h primes is the same, so they must equal one another. So b sine of c is worth c sine of b. Divide both sides by b little c, b little c. So sine of big C over little c is worth sine of big B over little b. And by the transitive property, since we already said sine of c over c is worth sine of a over a, we also have equal to sine of a over a. So that is our law of sines derived. So what they'll do is they'll call it asking us to solve a triangle. They'll give us basically a couple angles on the side or a couple sides and an angle. We'll start with the easier of the two, a couple angles and a side. So solve the triangle just means find any remaining angles and sides. So let's see, what will they give us this time? A is going to be pi over 9, B is going to be pi over 11, and little c is worth 8 in whatever unit of measure we have, feet, meters, yards, miles, millimeters, what have you. Well, we can definitely find cap c since we have two of the angles, and we know the three angles of a triangle have to add to 180 degrees, which is pi. So then c is pi minus the 2 we already know. So 99 is your common denominator. So 99 pi minus 11 pi is 88 pi. 88 pi minus 9 pi, 79 pi over the common 99. So we know the measurements of all three angles. So now we can get the remaining sides since we have one of the sides. So sine c over c is sort of our Rosetta Stone. It's the one that we know. So sine of 79 pi over 99 over side c is 8 is worth, we'll find a next. So sine of pi over 9 out of our unknown a. So we can clear the fractions out, and we have a sine of 79 pi over 99. It's worth 8 sine of pi over 9. So then a is 8 sine of pi over 9 divided by sine of 79 pi over 99. So there's our measurement for angle A, pi over 9, 79 pi over 99, not special angles. So we'll keep it there. That's our solution for A. And then we do the same thing with B. So keep the one that we know, sine of 79 pi over 99 out of 8 is worth sine of b over b. So sine of pi 11ths over the length of side b. So again, we cleared the fractions. So b sine of 79 pi over 99 is worth 8 sine of pi over 11. So then b is 8 sine of pi 11ths divided by the sine of 79 pi over 99. So now we found everything there is to find. We found angle C. We already had angles A and B. We found side A, side B. We already had side C. So we found everything there is to find about this triangle. We got the whole thing. So that's if they give us two angles and a side. If they give us two sides and an angle, there are different possibilities. It's quite possible that the two sides that we know, we'll just call them A and B, call this angle C. It's possible that our third side is not long enough to make a triangle. It's possible that we have exactly one right triangle. And it's possible that we actually have two triangles. So let's have our angle A here. And we'll call this guy angle B. So this is our side B, this is our side A. So two sides and one known angle. Now it's possible for me to make another triangle that has these two same properties. Length side B, length of size B, length of size A, and angle A included in here, and have it be a different triangle from the one in black. So there is one. I can do the extended one in red as well. This will still be length A. If you notice, this side triangle here is an isosceles triangle, so that means these two angles are congruent, since the two sides were congruent. And then we can get the measure from the fact that angle B plus one of these guys is a straight angle. So each of these guys is 180 degrees minus B, or if you like, pi minus B in degrees. Or in radians, my apologies, degrees back here already. So in either degrees or radians. So it is possible to have two different triangles that have these two sides and one known angle. And it is possible, though, that there is only one triangle. So either one right triangle, one non-right triangle, no triangles at all, or possibly as many as two triangles. And again, that's when we have two sides and one angle. We have to account for that possibility. So let's take a look at some examples and see how we would tell what's what. Sure, I'm framed nicely here. There we go. So I'll make little a 11, little b 7, and cap b 40 degrees. So watch your mode. If you're in degrees, make sure you're still thinking in degrees. If you're in radians, make sure you're measuring in radians. All right, so we can use law of sines. We know b the angle, and we know b the side. So we know sine of b over little b is worth sine of a over little a. And just fill in what we know. So sine of 40 degrees over 7 is worth sine of angle A over 11. So sine of A is 11/7 of the sine of 40 degrees. So sine of A. And for these, it's helpful to look at an approximation. So 11 divided by 7 times, we'll make sure we're in degrees. Sine of 40, again in degrees, it's approximately 1.01009, blah, blah, blah. It keeps going on. There's something wrong with that, though. Remember, if we have the basic y equals sine of x graph, the range on that guy was -1 to 1. We can't get something bigger than 1. So this one is a contradiction. There's a couple of common ways to write that. One is a circle with a little x through it. Another one, you can draw kind of two arrows butting up against each other. I've more often seen the short, easy to sketch one used. So this means, pardon me, if we get a contradiction, that means that there is no triangle with those properties. Not possible to do. So we'll try another one of these. A will be 6, B will be 3, and sine of A 40 and degrees again. So again, we'll use our law of sines since we know sine of A and we know little a. So sine of 40 in degrees over 6 is worth sine of big B over 3. So sine of big B is 3/6 or 1/2 sine of 40 degrees. So I'm going to run that through the calculator for just an approximation, just to make sure that we don't have this other case of no triangle again. So 1/2 sine of 40 degrees, we're at roughly 0.32. It keeps going and going, but that is on the -1 to 1 interval. So we do have a triangle. So we have at least one triangle, maybe more, but we have at least one triangle. So then if I want to find angle B, then angle B would then be the arcsine of 1/2 of sine of 40 degrees. So angle B, approximately, running that through the calculator, 18.747 in degrees. Quite possible, no problem there. So then we want to see, okay, is this one triangle or two triangles? So 180 degrees minus 18.747 degrees. So we're at about 161, 161.253 degrees. So this is a possible second angle B. We'll call this B sub 2. All right, so let's continue with, let me just refresh what we know. So little a is 6 for this one, little b is 3. Sine of cap A is 40 degrees. And angle B is approximately, not sine A, my apologies, not sine A. Cap A is 40 degrees. I'm not sure why I wrote sine A on there. Cap A is 40 degrees. B, approximately 18.747 degrees. Angle C, we would just do 180 degrees minus the 2 we know. So $180 minus 40 minus 18.747, and angle C then uh, 121.253 in degrees. So that's quite possible to do. Let's check our alternative as well. A is 6, B is 3. A is 40 degrees. And our B sub 2, if B sub 2 exists, we said it was 161.253 degrees. So angle C then, or C sub 2 if you'd like. So that would be 180 degrees minus A minus B. But once we do that, 180 degrees minus 40 minus 161.253, we get into C2 being a negative value. So if the third angle has to be a negative angle, that means there is one triangle only. C2 can't be a negative. So we have our A, we have our B, we have our 3 angles. So we're just looking for then angle C. So we'll go with what we know. Sine of 40 degrees over 6 is worth sine of C degrees, so 121.253 degrees over C. So then C is worth 6 sine of 121.253 degrees over sine 40 degrees. So approximately 7.980. So we have our 3 sides, we have our 3 angles, and it was one triangle only. Coming up with a negative value for an angle is a contradiction, just like coming up with a sine being off of negative 1, 1 is a contradiction. All right, so one more, same direction, solve the triangle. So A is 10, B is 12, cap A is 25 in degrees. All right, so this is another situation where we had 2 sides and 1 angle. So that's when we have the different possibilities where we could have 0, 1, or 2 triangles. All right, so we'll first figure out what angle B would have to be worth. So sine of 25 in degrees over 10. Sine A over A is worth sine B over B. So sine of cap B over 12. So sine of cap B, 12 tenths or 6 fifths of the sine of 25 degrees. We'll key that in and make sure that we're on the proper interval. So 6 divided by 5 times sine of 25. Make sure you're in degrees. And we're approximately 0.507. That is definitely on our range of -1, 1. So we're good on that. So that proves that we do have a triangle that exists. So next we'll find out what angle B is worth. So B is the arcsine of 6 fifths sine of 25 degrees. So B is approximately 30.474 degrees. So angle C, angle 180 minus angle A minus angle B. So back 80 minus 25 minus 30.474. Angle C approximately 124.526 degrees. So we have at least one triangle with it. Now we want to see, do we have two triangles with it? If there are two triangles, then the new sine B would be 180 degrees minus B. So 180 minus the minus the 30.474. We're at about 149.526 in degrees. That's possible. That's not more than 180 degrees. So then C2 is the big check. That would be 180 degrees minus measure of angle A minus angle of B2. So 180 minus the known 25-degree angle for A minus 149.526 for angle B2. And we're still in the positive. So C2, 5.474 in degrees. So we have then two different possibilities for little c. So we'll take a look at each one of those. So for the first possible triangle, sine of 25 degrees over 10, so sine of A over A is worth sine of C over little c, so sine of 124.526 degrees over little c. So c is 10 sine of 124.526 degrees over sine 25 degrees. So that's our exact. If you want an approximate, 10 sine of 124.526 degrees divided by sine of 25 degrees, about 19.494. We do have a different possible little c. We'll call that one little c2. So same known one, sine 25 degrees over 10. It's worth sine of our other possibility of c, 5.474 degrees over little c. So little c would be 10 sine of 5.474 degrees over sine 25 degrees. So our other possibility is that C, we'll call this guy C sub little c2. Little c2 could be 2.257. So two different possibilities for this triangle. So it's possible to have no triangles, one triangle, or two triangles when we have this special case of side-side angle. So in 8.2, I would recommend 9 to 37 on the odds. If you are trying the MyMathLab, I'll try to upload similar problems on the MyMathLab. If you have any questions, get in touch with me. Otherwise, I'll see you next time. Thank you.